Hello everyone, today I'm going to talk about the overfitting and underfitting, which is the most common issue in the machine learning project. We are going to talk about the how to find the overfitting and underfitting and how to solve it. So let's get it. Suppose you are going to build a model to recognize a ball. Well, teaching a model is very similar to teaching a baby. So if you have a baby and want to teach it, this is your ball, how will you do it? Well, you can see the balls in your home like the baseball, basketball, and the soccer ball. You will find the common things from these balls. And you will eventually find that, okay, these balls have the rounded shape. So teaching a baby like these rounded shape objects are balls. Just like this, you can teach your machine that these rounded shape objects are ball. Okay, so you can test your robot now. Showing the baseball and your robot is saying that this is a ball, this is a ball to soccer ball and the basketball. So far so good. But you will eventually find that your machine just keeps saying this is a ball whenever the object is in the rounded shape for apple or even a full moon. So this is totally wrong. You are going to find out more common features from the ball, and you eventually find that you cannot eat the ball and you can play with ball. So apple, you can eat it, so it's not a ball, and the full moon, you cannot play with it, so it's not a ball. So now you know that your machine previously was too biased on the round shape. Now you have three features here, and the previous situation we call underfitting. When the model was too biased on something, then we call it underfitting. Well, now you teach your machine with three features here. Round shape, you cannot eat the ball, and you can play with ball. And eventually the prediction is so good. You can see these are all balls for the baseball, soccer ball, and the basketball, and your machine also predicted well on the apple and the full moon. These are not the balls. Well, here another situation. What if you teach machine with too many features from the given data? Well, as I told you, then we have the baseball, basketball, and the soccer ball at home, and you want to get more common features from this trained data, like the ball has stitchy, and these balls have the greater than the 70 millimeter in diameter. For example, the baseball is something like the 70 millimeter diameter. So you train this information in your model, and if you test your machine that, the thing is this machine is still good on the trained data. This machine is saying that this is a ball for baseball, soccer ball, and the basketball. But the thing is, if the machine went to outside and see some unseen ball, like the golf ball or the ping pong ball, then the machine will say that these are not the ball because these balls is very smaller than the 70 millimeter diameter and doesn't have stitches, right? This makes sense. So this situation we call overfitting. When your machine had high variance, we call it overfitting. So I keep saying the bias and the variance because these two terms are key factors to fix the overfitting and the underfitting. So what is the bias and what is variance? Where the bias measures how far off in general these models' predictions are from the correct value, and the variance is how much the prediction for a given point vary between the different realization. So here's a good visualization to explain this one. So high bias. So in the underfitted model, you can see this red point is the correct value. But your predictions, the blue dots here are far from the correct value. This is underfitted model. For example, our model like the which trained with just a round shape is a ball. Well, it's not working well, right? It's not working well. It's far from the correct value on the training and the tested data also. And when the model is overfitted model, that means high variance. This model working well on the trained data, seen data. You can see some predictions are in this red dot, but for the unseen data, the prediction is totally wrong. So our goal to train our model is going to be like this: low bias and low variance. Since the bias and the variance are the metric, something is the mathematical, the quantitative term, we can use this terminology to overcome the overfitting and underfitting. So let's take a look at this graph first, bias variance trade-off, which is great graph for you. So the first situation when we train our model, we just said that round shape object is a ball, right? We just had one feature, so we had just one feature, so there's a high variance here and low variance, high bias and the low variance here. And since it was underfitted, the error rate was very high. And we eventually gave more features like the you can play with ball and you cannot eat the ball, right? So variance is going lower because we gave more features, and the variance is going a little bit higher, right? And the error rate was going down like this. And that this is the best error rate, which is the minimum point of the error rate. This is the best model for you. But if you give more features like the from your train data, like the have the stitches and the diameter is greater than 70 millimeter, then the bias is going up eventually, right? And the bias is going down. Variance is going up and the bias is going down. And the error rate is going up because this model now is working very well on your training data, but it's not working well on the unseen data like the ping pong ball or the golf ball, right? Error rate is going up. So this model we call the overfitted model. So the goal of the train is to find this fit point between the bias and the variance here. So how to overcome the underfitting? Now we know the overcome and the underfit, and now we know the overfitting and the underfitting. So now it's time to understand how to overcome underfitting first. Well, you already saw how to overcome the underfitting, right? So when we taught the machine that the rounded shape is the ball, it was a high biased model and was underfitted. And how we solved this problem, we gave more features like the you can play with the ball and you cannot eat the ball, right? So finding more features. Finding more features will lower the bias and give a little bit higher variance here, and you can eventually overcome the underfitting here. And also you can try with the high variance machine learning model like the decision tree, KNN, and SVM. Well, now let's take a look at the overfitting. Okay, so how to find if your model is overfitted? Well, this is very easy to find actually if your model is working well on your trained data, but it's really bad on the unseen data, test data. There's a highly chance that your model is already overfitted. So in order to fix this overfitting issue, the first thing you need to do is to have the validation step with validation data. How to do this? One of the state-of-art technology is K-fold cross-validation. So let's suppose these data are your the scene data, your data, and if the K is 10, then you have the 9 subset of train data and 1 subset for validation. So you train with this 9 subset and test against this yellow subset here. This is the first round, and the second round you use another validation set, this yellow part, and using the other blue sets you train. So if the K is 10, you will get the 10 validation accuracy here. You can sum and divide by the K, you will get the final accuracy. So you will get the final accuracy here, and if the validation final accuracy is lower than the train accuracy, then you will need a regularization in order to overcome the overfitting. Okay, so how to do the regularization? I will do this on the next page. So repeat the regularization until there is no overfitting. So this is time to understand the regularization. In order to understand the regularization, the best classifier is the regression like this. So for example, your regression model is like the right hand side this model. So you have the observed data here, and your model is like this zigzag line here. This is very overfitted model. You probably want to have some general line like this. So how can you make this zigzag line to be simpler like this line, general line? Well, you can use the regularization here. So in order to understand the regularization, you need to understand the cost function first. So this is the cost function of the regression. This is nothing but the difference between the hypothesis and the real data. And you want to minimize this one so that you can get the best line for your observed data. So if you don't have the regularization, the regression line will be like this. and we want to simplify this line. How? We can use the regularization here. So I'm just adding this term here, like the 100 multiplied by the theta 1, theta 2, theta 3, and theta 4. Theta stands for the coefficient of your regression function. For example, the left-hand side, this function is the original regression function, and I just changed the coefficient of the regression function. Like it was 0.1, but I changed it, giving just the half size of the coefficient. And what's the difference here? The original function was like this, but if I give half size of the coefficient, the line is more smoother line than the original function. You can see the gradient of this line is smoother, is less than the gradient of the original function. So since the gradient is less than the original one, the variance is less than the original one. So by giving the less size of the coefficient, you can give smoother line on this regression. This is it. That's it of all of this concept of the regularization. By giving this term in the objective function, minimizing this j data, we can give some less value on the data 1, data 2, data 3, and data 4 here. So this is the formal equation for the cost function with regularization. So lambda here is the learning rate, and we are just summing up all the coefficient and multiply by this learning rate. So let's get back to the regularization example here. If your original regression function line was like this, and in this time you probably have the very small learning rate or 0 in the learning rate, or yes, that is it, right? So if you give some value in the learning rate, something optimal value in the learning rate, you will have the smoother line like this. And that if you give too high value in the learning rate, your function will be like this linear, which is underfitted model. This is most of it of the regularization. Okay, and the next concept is early stopping. In terms of the deep learning model, there is a state-of-art overfitting overcoming technique. One of the technique is early stopping. Deep learning model trains with iterative training, which is epoch concept. If you just have many epochs, well, will the deep learning model has good prediction? The answer is no. So for example, if you have enough count of epoch here, like this, enough count of epoch, enough count of the iteration, your training accuracy and the validation accuracy will go high like this. So this is your best model. But if you keep iteratively train on your trained data, you are going to overtrain on your trained data, and your validation set accuracy will going lower because your model is already overfitted. So the best way to have the best model from the deep learning is to early stop when you have the best accuracy here, right? This is the concept of the early stopping. Well, the second concept is dropout. Well, dropout is a state-of-art overfit overcoming technique by selecting some neurons randomly during training. So for example, here I'm going to mark. So first iteration, you can use this neuron, and this neuron. Second, well, you can use this one, and this one, and this one. And the third iteration, you may use this neuron, this neuron, something like this. So conceptually, this is how the dropout is working. And do you think this will help to overcoming the overfitting issue? Yes, it helps. Well, because first subgroup neurons are working like ensemble. That means less variance and less bias. Because it's slipping some training, the variance is going to be less, right? So less variance means it's farther from the overfitting issue. And second one is the neurons not overtrained on given data because they slept sometimes, right? So they just missed some training. That means it has less variance than the no dropping out model than the standard neural net, right? So this is it. I covered all the overfitting, underfitting, overcoming technique so far now, and I hope this helps you to understand the overfitting and underfitting and how to overcome these kind of issues. Thank you for watching, and I will see you on the next video.